Our next speaker is Paul Cole from Skanska, who's going to take the theory of what you've just seen to a practical trial that's been carried out on the M42. Paul.
Thank you. Welcome to this session on the practical application of basalt fibre reinforced concrete trial. I'm conscious that I stand between you and lunch, so I will try and keep it moving as quickly as possible. But I have to start, and I know you should not start any presentation with an apology, but I must apologise to Rachel. Because when I gave her a hard question, I suddenly realised that I was going to get up and speak. And I may get one or two back. So Phil, start thinking of your difficult question now, because you started it. So we'll see where we go from here. Okay, so 20 minutes or so, and maybe a few minutes for questions. I might just hang it out so we don't get any questions. My name's Paul Cole, Chief Engineer for Skanska, and I'm supported today by Robert Gosling, Head of Commercial and Engineering Solutions from Tarmac. I also have Nathan Busby, who's my Head of Materials Engineering in Skanska, who will also deal with any difficult questions that you have later. Just a quick introduction to the trial. Why were we doing it? Who were we doing it for? National Highways sponsored us under their designated funding. So a fully financed trial funded by National Highways, part of the consortium. The rest of the consortium, led by Skanska, was Tarmac, BASTEC, Basalt Technologies Limited, who provided us with the basalt fibre reinforced polymer, and also the National Composite Centre based in Bristol, who deal with all sorts of composite materials and were very advantageous in the consortium. So I'm sure many of you will be familiar with this document, Construction 2025. It lays out a number of challenges. The government produced this in 2013. We are almost at 2025 now. But they set some very high-level key targets. Lower construction costs by 33%, deliver projects 50% faster, lower environmentally harmful emissions by 50%, and also close the gulf between imports and exports. Well, I think this trial pretty much covered three of those areas. And it also supported Skanska's drive to be net zero on all projects by 2045. The challenging part of that is that it includes the supply chain. So if you're supplying Skanska materials, you're going to have to be in that target as well. So if we just take a quick look at materials themselves, obviously getting to net zero includes a lot more than just materials. But we perhaps should start with the efficient use of the materials we already have. That seems like a logical place to start, followed by a rapid introduction of low-carbon materials. Increase in investment and research is going to be essential to drive those materials down to being carbon zero. And once we actually get there, we need to strive for an industry that has a highly optimised use of those carbon zero materials. So where does this trial sit? Pretty much at the beginning of that step number 2, just a simple introduction of some lower carbon materials. So, just in a few scene-setting words on concrete, we have, and this aligns with some of the other presentations that we've had today, is that cement is responsible for 4 to 8% of the world's CO2 emissions. It's a rough number. I think it was mentioned earlier today that it sat at about 6%, so it's smack in the middle of that number there. But amongst materials, only coal, gas and oil are a greater source of greenhouse gases. Roughly half of concrete's CO2 emissions are created during the manufacture of that concrete cement clinker. We've heard that today as already. The most energy-intensive part of that cement-making process, so therefore it contributes to 2 to 4% of the global CO2 emissions. A significant number. But for comparison purposes, I just want to say that in the UK, it currently sits at about 1.5% of our carbon CO2 emissions. And I've got the figure of 65% of that is down to the breaking down of the limestone. We've seen the number of 67% again already today. So we're talking the same figures here. That's a very energy intensive process. And in terms of good and bad, you could say that the UK is only less bad than other parts of the world. But we still can't claim to be anywhere near good, and much more needs to be done to make those emissions acceptable. But there is hope. There is hope. You can use an alkali activator in place of cement clinker. This reacts with other materials holding pozzolanic properties, such as PFA, GGBS, or calcined clay. So let's move on to the trial. 4 8-metre by 4.5 metre wide reinforced concrete ground-bearing slabs were constructed on National Highway's M42 Junction 6 project near Birmingham, a scheme that's being delivered by Skanska as part of the National Highways Regional Development Programme. The 4 slabs created a 32-metre long concrete haul road over which all construction plant and deliveries were to pass during the construction phase. 2 types of concrete were used, a conventionally used C3A blended concrete mix, something I'm sure you're very familiar with, and the lowest carbon concrete currently available in the UK, which uses an alkaline activator. That kickstarts the pozzolanic reaction within the other materials, in our case, GGBS. So AACM concrete is the only ICE A double plus concrete available right now. Carbon Concrete Zero are already reclassifying that as market-beating products. But whatever you call it, it's the lowest carbon solution that we currently have in the world of concrete. It shouldn't be long before it becomes an accepted and, I believe, the responsible choice for delivering our concrete structures. But it's not really the end of the story. We could certainly be responsible by using it. A bit more about that in a few slides' time. But I think it's each of these concrete mixes we reinforce with different reinforcing bars. Steel reinforcement and basalt fibre reinforcement. So basalt fibre reinforcement being lightweight, corrosion-free, and steel being the conventional product that I'm sure you're all very familiar with. So this trial was the first to combine these 2 materials. You may well have heard of AACM concretes and basalt fibre reinforcement, but the combination of the 2 was something new. Basalt rebar has been used in the rest of the world. There are codes that you can use to design to it. The same applies for AACM concretes. Unfortunately, we're not so fortunate in the UK. We don't tend to have the design guides and codes that we require. But the rest of the world are ahead of us, it has to be said, and we are playing catch up. Okay, so there's a big blocker. In an effort to try and drive things forward, the trial on the M42 was set up to provide these, to try and break down the blockers, the biggest blocker being the fact that we don't have the codes. So what do we actually do? What do we actually do to actually try and improve that situation? And there are things that are already being done, and that's good news to hear. And if we just take a look here at some of the stuff that Tarmac are actually doing at the moment. You know, I don't work to notes, but I wanted to keep to 22 minutes. So we'll see here how I've managed to move away from that. So as I'm sure you appreciate, there are byproducts. GGBS and PFA are byproducts of other highly carbon-intensive manufacturing and energy-hungry processes, both of which use fossil fuels. So if we're proposing to replace some of the cementitious material in our products with these byproducts, we're just taking carbon from one place and moving it to another. From a commercial perspective, until very recently, GGBS went through a bit of a supply and demand turmoil, which resulted in it becoming more expensive than CEM 1. So not exactly attractive from a cost point of view. We import most of what we use, which adds another carbon factor to the consideration. And there will not be an exhaustive supply of GGBS for the future. In the trial, we experienced some very low or some lowish early strength gains. And we experienced a powdery surface, that latence, that powdery surface, which you can attribute to a high GGBS content mix that I'm sure you're familiar with. Tarmac, however, have adopted Wagner's blended alkali activator in liquid form, which disperses much more easily and readily through the mix. And combined with specific admixtures, they have also successfully developed a mix that incorporates up to 70% of PFA. That particular solution has been seen to deal with the low strength gains and also managed to remove that powdery latence effect that you tend to see with GGBS mixes. So, replacing GGBS, PFA, with UK green energy produced calcined clay. I mentioned calcined clay just in passing in our previous slide. But is that an option? Is that an option for us? And is it available to us now? Well, in practice, actually, calcined clay, again, is being used in other parts of the world, but not currently in the UK. But it has the pozzolanic properties, and we have copious supply of clay in the UK, but we don't manufacture calcined clay in the UK at present. I believe that Tarmac's facility for doing so comes online around 2028. So maybe the use of alkali activators with GGBS or PFA is a stepping stone to a more carbon-free solution for the future. So back to our current reality for a moment. As I mentioned previously, AACMs are not yet codified in the UK. So just very quickly, EN 197 and BS 8500 do not yet include for AACMs. However, PAS 8820 gives guidance on suitable performance criteria, and BSI 350 is in the process of being developed, which is a performance-based standard for use of AACMs. Have to watch that space. So, moving a little bit into the area of the basalt combined with the AACM, what kind of CO2 reduction do you think is achievable through the combination of the two? Well, overall, the conservative figure would be a saving of about 50% CO2 saving. The trouble is nailing down the baseline product that you're comparing to. So when did you last use or perhaps specify a CEM 1 concrete mix? We've heard the comparisons to CEM 1 a fair bit today, but I don't remember the last time a straight CEM 1 mix was used. Well, if you did, then the baseline of ACM concrete would give you an 80% saving. We can claim that. I'm sure Tarmac will shout that from the rooftops. But actually, the reality is going to be somewhere less because we're likely to be measuring it against a more conventional blended concrete mix that we would generally use. But the saving is still significant. Basalt fibre is also around 40 to 50% saving. But what are we comparing that against? Steel manufactured in what sort of way? Is that 100% recycled steel? Electric arc furnace process? Well, obviously, if that was the case, the saving would be at the lower end of that spectrum. But nevertheless, a conventional saving, a significant saving. So what are the other benefits? Corrosion-free, we just heard that in the last presentation. It's a significant advantage, particularly when we're looking at reinforced concrete roads. Remove the corrosion, potential for corrosion in the reinforcing bar, and that explosive nature could be removed, reducing maintenance significantly. But there's also lower weight bars, transporting these bars with less deliveries, making productivity better on site, fixing more rebar more quickly. I think those things, particularly for contractors, are significant. And I just briefly look at the low hardness, that fibrous nature of the basalt fibre bar. Part of the M42 trial was to deconstruct the slabs that we've constructed using a conventional road planer. Basalt was a rock. Basalt fibre reinforcement has come from being a rock. The intention was to plane the concrete road up and create a 6F2, Site 1 6F2 material for using elsewhere on the project, or perhaps for sale and transportation elsewhere as a 6F5. But actually creating that material graded through the adjustment of the planer in one move, one action, one process, could be quite significant for the ongoing use of it as a construction material. So, upon initial inspections, well, sorry, before I get on to the outcomes, I just need to mention that there's actually a quite a detailed report, and I'm just skimming over the headlines of it. If anybody wants a copy of that fairly comprehensive report, then it's available for you. Just get in touch, I'll forward it. Okay, so they're the areas that the project has covered. Just in briefly. I'll look at the recommendations for further research in a moment, some of the conclusions that we drew from the project, but just a few figures. Project outcomes, flexural strength, shear strength, and pull-out. Very quickly, on the shear strength, you can see the figures in front of you there. A few of those columns are important. It's 110 kilonewtons, 141 for steel and basalt fibre reinforcement, respectively. And ASM panels reached a maximum load of 97 and 106, respectively. Now, it needs to be noted that the concrete strengths, although we were aiming for a 28 Newton concrete, the actual strength of the concretes were different. So the C3A reached 44, the AACM reached 34. It's not because we couldn't have the strengths. We were actually aiming for a low-strength concrete in this trial because on site we wanted to see the performance, and we wanted it to crack. We wanted to see how much load it could take. Would one perform better than the other? We could have put a very high-strength concrete in and not seen any detrimental effect for the next 25 years, but that wouldn't have been very helpful. So you can actually see from this that both the basalt fibre reinforced slab and the steel reinforced slabs performed very well. And I was quite pleased about that. I was quite pleased about that because it actually demonstrated that although you have a different E-value, as we've just heard, and you've got a more fibrous nature within the basalt fibre reinforcement, the performance when in the matrix of concrete was very good. I'm going to move on quickly. How are we doing for time? You all right? Yeah. Okay. So for shear strength, these were even more interesting because if you actually take the pure shear value of basalt fibre reinforcement, it's not very good. And it's very difficult to use design codes to design a structural member using the shear values that you will find for pure basalt. It's not a homogeneous material, it's a pultruded construction method, so all the strands are laying in one direction. So you could basically cut through them quite easily with a knife compared to steel. So it's currently, without the codes and standards, it's very difficult to design using basalt. But these large life-size scale tests in the laboratory were really quite useful. And you can see that the performance of the basalt fibre reinforced AACM or C3A performed extremely well against the steel reinforced concretes in shear. It's fair to say that the mode of failure is different. The mode of failure is different because whether the tensile or shear tests, the failure in the bar is brittle within the basalt fibre reinforcement. It's far more ductile within the steel. So the design has to be delivered in such a way that the designer understands that. Designing elements for the concrete to fail rather than design it for the failure of the rebar. We don't want sudden catastrophic brittle collapse of structures. So designing it where the concrete strength is the controlling element of the design. Pull-out tests. We did our best to meet the British standard for this with the steel coils that you can see within the sample. But unlike the basalt fibre reinforcement that you can see outside in the entrance, these bars had a helical strip attached to the outside of the bar during the after the pultrusion process. So it's essentially welded to the outside of the bar using the polymer. They're sand coated, the bars outside, and I'd be very interested to compare the difference in performance between the helical bar and the sand coated bar, because we did see some slip in these results. Even though the final performance, the ultimate failure in the pull-out test, as you can see, were extremely comparable between steel and basalt. The graphs, if you read the report and look at the graphs, the detail, it gives you an indication that maybe there's a little bit more slippage going on in there with the basalt bar, with the helical winding. So a bit more further research required. So on that point, and I won't go through every item in detail verbatim, but pull-out tests with varying reinforcement diameters and embedment depths, and also looking at the difference between sand-coated and the spiral windings, I think are really important. And there's steps we can take in perhaps introducing a lower carbon resin. That's really where a lot of the carbon sits with the resins used in this product. And with the AACMs, we have to understand not just longevity, but how does it perform in different temperatures, extreme cold and hot. Early life surface abrasion is one area that we saw some issues with. But I think there is some major steps that the industry can take. If you take a continuously reinforced concrete pavement made from an AACM, an alkali activated cementitious concrete that actually incorporates calcined clay, reinforced with a continuous basalt fibre reinforcement bar, which is then actually surfaced with a thin surface of asphalt. And this is where we're looking now at our next trial, is that we're working with a company called Low Carbon Materials that is looking to introduce a low percentage of a carbon negative aggregate into an asphalt mix. The carbon negative aggregate, proportions of about 10%, offsets the carbon in the rest of the asphalt to make it a carbon neutral solution. If you put a thin surface asphalt over a low carbon basalt fibre reinforced concrete pavement, clients should responsibly be all over that. Thank you. Any questions before? And they are. Well, I did one. It's good.
How much of that have you actually laid on the M42?
How much of that have you actually laid on the M42, and is it still there, I suppose?
Yes, it is. Yeah, you could pop there tomorrow and see it. Yeah, it's. We are looking to deconstruct it very shortly because the project's coming to an end, but it's been there for the best part of a year, and it's 32-metre long haul road, and it's in our gift as the principal contractor to use it in temporary works. And because of the lack of codification, lack of standards, if you wanted to incorporate in permanent works, there are far too many obstacles to get it there quickly. So in order to move things forward as quickly as we can, we decided to incorporate it in temporary works because we could, and just test the hell out of it.
Regarding the trial, have you tried to include standard mixed design with standard heat? Yeah, have you tried to include standard mixed design and this activated mix with standard steel and compare the result under traffic? Is there any indication of early failure?
No indication of early failure. We did 4 slabs. Each was 8 metres long, 4.5 metres wide. We had two concrete mixes. One was the conventional C3A, the other was the AACM. And we reinforced both mixes with steel and basalt. So 4 slabs with all the combinations. The 2 steel reinforced slabs were doweled together using steel dowels, and the 2 basalt fibre reinforced slabs were doweled using basalt dowels. And we simply observed the performance. The trouble with any road on the network is that it's subjected to many more million standard axles than you could possibly get across a concrete haul road. We had very heavy deliveries, as you would imagine, but actually in real terms, not that much loading, which was why it's very difficult to observe the performance of the road in real time. But we did our best to just see how it handled. In fact, Phil's question from the last session was about, have you actually laid the basalt? Well, we thought it was useful in itself just to handle the basalt, place the basalt, handle the AACM concrete, pour it, see how workable it was and how easy it was to place, that sort of thing. So yeah, we think the trial was about as far as we could go with the time and money we had.
I think the point, any trial, from design point of view, you need to test it to failure, and that's what you mentioned. You have low strength. Usually, you can construct low support to create flexural strength, so you can observe it to failure. Doesn't need to represent the actual design, but when you see how many load application till failure compared with the standard design, you can quantify the benefit or reduction in life. But you don't have enough traffic to observe that.
No, but what we did was those samples that you saw in the laboratory, we cast those alongside the slabs on site, so they were live, only metre wide rather than 4.5 metres wide, but their overall thickness and reinforcement was exactly the same as the site trial, and put them on the back of a flatbed and all the way down to BRE to do the testing in their laboratory. And the difficulty we had was actually the setup. The transducers weren't large enough to allow the deflection to go to complete failure of the bars. But in both the steel and the basalt case, it was the concrete that failed first.
One final question.
No, you had the hardest question. I believe that's you. Yeah. Are you ready for this?
So it seems to me like for AACMs that the freeze-thaw resistance for kind of horizontal surfaces, slip-form barriers is going to be the biggest blocker.
It could be.
Do you see a solution
Yes.
to that with these?
I was conscious of time and trying to shoehorn everything into the presentation, which is why I alluded to the fact that actually maybe we should be looking at thin surface, asphalt surface courses on top of the concrete, because that is easier to maintain, easier to repair, will, I believe, deal more easily. It will protect the concrete, which is more difficult and more expensive to repair than an asphalt. So a thin surface would give the public a surface that they are perhaps more comfortable with, quieter. If you needed to repair it, you're not into longitudinal grooving, but you're into perhaps planing and replacing that thin surface. So if that thin surface was carbon neutral, then I believe that's the future of concrete roads, personally. But that's just my view.
Well, thank you very much.
Thank you.